As we said, in addition to covalent bonds, ionic bonds sometimes strip electrons from their bonding partners. I was referring to it as donating an electron before. An example would be the transfer from sodium to chlorine, as we had just mentioned. So, a charged atom, and this will be important eventually, a charged atom is called an ion, but you can have two different charges, of course. So, a negatively charged ion is called an anion. A positively charged ion is called a cation. Okay, so an ionic bond is an attraction between an anion and a cation. So, in our example, sodium, which was positive after it gave its electron to chlorine, would have been, right, a cation. Chlorine, because it was negative, it took an electron from sodium and therefore gained a negative charge, is called an anion in that case. So as you can see here, as you can see here, sodium gives it to chlorine, right? That removes a negatively charged particle from sodium because electrons are negative, making sodium positive. And since chlorine gained that electron, it got one more negative charged particle, it is now negative. Positives and negatives attract, and therefore you have an ionic bond formed between them. These ionic bonds are often what result in the formation of crystals, right? So, salt can form a crystal. You pour table salt, and, some of it lands on the napkin next to your plate or something like that. They look like little cubes. Well, that's why they look like cubes, because you have this ordered arrangement of sodiums and chlorines all stacked within each other, all together, which make this cubic formation of the crystal. That's why crystals are whatever shape that they're in. Every different compound is going to have a different shaped crystal, and sometimes even the same compound can have multiple types of crystals that form it. Think about like gemstones versus the little minerals and stuff you might see. I don't know, in the ground and rocks when you break them open and they shine in the light. Okay, weak chemical bonds. So these are not covalent and these are not ionic, but weak chemical bonds, I like to think of them as like Velcro. Okay, so some of the strongest bonds in organisms are covalent. So we already said that, right? Weak chemical bonds, such as ionic, which we've already talked about, and hydrogen bonds are also important. Hydrogen bonds are kind of like Velcro. They're not very strong individually, but if you add them all up together, it actually can result in a pretty strong bond between two molecules, right? So if you think about Velcro, if you really looked at Velcro, those when you had those Velcro sneakers before you learned how to tie your shoes or something, right? There are little hooks on one side of the strip, right? And then there are little loops on the other side. When you press them together, some of the hooks hook into the loops and therefore hold everything together. Now, one loop and one hook would be really, really weak. But if you put a ton of them together, that actually can add to a pretty strong bond, right? So that's what we're talking about here. So hydrogen bonds are a form of those weak bonds. They form when a hydrogen atom, remember these are the smallest atoms on the periodic table, covalently bonded to another one, is also attracted to another electronegative atom. Okay, so in other words, not the bond that the hydrogen is making with whatever atom it's bonded to, that hydrogen can still be attracted to other molecules in the nearby area. Okay, so in living cells, these electronegative partners that forming these hydrogen bonds, right, are oxygen and hydrogen or nitrogen and hydrogen. Those are the ones that actually will attract each other and kind of like, hold together a little bit. Very weak on its own, but if you add enough of them together, it actually leads to a pretty strong bond. This attraction will weakly hold the two different atoms together and thus hold the compound these elements are in loosely together. So these are two different compounds being attracted to each other, right? DNA, which is pretty much the longest molecule in the body, is held together by hydrogen bonds. There's just so many of them that it holds DNA together and it's nice and stable. We'll talk much more about that later in a subsequent chapter. Okay, so what I'm saying here is, here we go back to our water molecule, right? You have the negative side, that's where the oxygen is, that's the red. The positive side, hydrogen, that's the white, right? But because this hydrogen is positive, and obviously you have a lot of water molecules together, right? Because this hydrogen is positive, it can be attracted to this relatively negative oxygen on another water molecule, okay? And the same thing is going on up here. You see how the oxygens, the reds, are always facing the whites, right? So red to white, red to white. This is why water is relatively sticky to itself, right? So in other words, you know, uh, so I guess, the best way to think about this is, if you were to push two drops of water together, right? You put them on wax paper or on, you see it going down your windshield when it's raining or something like that. When two water drops meet, they'll bond together, and make a bigger droplet. This is also how, if you think about it, raindrops form in the atmosphere, right? You have all this water in a gas form and they start to stick together and form a liquid drop, which eventually falls out of the air as rain. Okay, so van der Waals interactions are relatively weak forces that occur, kind of like hydrogen molecules. So, or sorry, hydrogen bonds rather. So, molecules or atoms that are very close together can be attracted by these really, really quick little charge differences, and we call those van der Waals interactions. The interaction is very weak, but if you add again enough of these together, you get actually a pretty strong bond. What you It's weird, but what you're seeing here in this picture right here are different toes on geckos, right? So gecko's like a lizard. Think like the Geico commercials, right? They have these little pads on their feet, and depending on what type of gecko you have all this foot diversity here, right? If you were to take an electron microscope and look at them really close, you'd see all these little tiny fibers. Well, these little fibers can bond to a surface because they are also made of atoms and electrons too, right? This is how a lot of organisms can like walk straight up a wall or even like land on the ceiling if you're talking about an insect or something, right? These little tiny weak forces between each one of these little hairs on the toes, right? So this picture over here would be like an inset of just a little tiny portion of a toe here, right? That allows enough force for a gecko, to walk up a wall. So shows you that, just these combination of forces are actually pretty important. Whoops, sorry about that. So the last thing I want to talk about is molecular shape. Okay, so the shape of a molecule directly affects its function. All right. So how molecules interact in a living thing, or actually anywhere, is by their shape and their charge. All right. So a molecule's shape is determined by the number and type of atoms that make it up, right? That will determine what positions the atoms get into and therefore the shape of the whole molecule. So in a covalent bond, or covalently bonded molecules, you can actually get a probably infinite number of shapes of different molecules depending on how many atoms you add to them and how they bond together. Okay, so what I'd like to show you is this right here, this crazy molecule. Now, obviously, I'm not going to quiz you or whatever on this, but you can see that the carbons are there, there are hydrogens there, oxygen, sulfur, nitrogen, all these things that are all bonded together, right? Well, this little piece right here has a specific shape, right? I can't describe that shape, but there's 6 hydrogens, 1 oxygen, and 5 hydrogens in this square. Okay, well, that's a natural endorphin. Okay, so what's an endorphin? Endorphins are happy hormones, right? So, you may have heard of these. They're chemicals that your body produces, like serotonin, dopamine. These are the chemicals that are released in your brain that give you that satisfaction feeling, right? It's like, you just ate a big meal or you just, did something that was really, really satisfying. Somebody retweeted this tweet that you put out there a million times. You're like, wow, I'm pretty cool, So you get this little surge of happy hormones in your brain, and people really like that. The reason that it works is because it's a specific shape. At least this little portion of the molecule that has the square around it is a specific shape. Well, unfortunately, or maybe fortunately, morphine and other opioids mimic this shape. Okay, it's not exact, but it's close enough where it'll work the same way in the body as natural endorphins do. Okay, so in other words, what I'm saying here is if you have morphine in your system, you're going to have that sort of happy hormone sort of rush, right? And keep in mind, the amount of morphine you put in your system is only limited by how much morphine you got in the syringe, right? Normally in your brain, you're only producing super tiny amounts of this endorphin, but morphine, can occur in, huge amounts, right? Depending on how much you give. So if you think about it, what's happening here, and I know I haven't really talked about this yet, but this is a cell, right? So this kind of like arch here, kind of looks like a rainbow going across the screen, right? This is a cell, and it's got these little receptors in it. Once a natural endorphin bonds to the receptor, the brain cell, for however this works, and I don't know if it's ever really been sufficiently worked out, has that satisfied feeling to the rest of the brain cells in the body, right? Well, if you add morphine and it bonds the same way, so you can see kind of like they fit the same way together because of the shape, you'll get that, but the more morphine you get in the system, the greater that happy feeling is. And this is honestly what leads to addiction, right? People love feeling satisfied like that or having that just that rush of euphoria. And that's what, unfortunately, what opioids can lead to, which I don't probably have to tell anybody in class. That's primarily what led to the opioid crisis that we've been having, you know? So chemical reactions, I just want to, kind of like end it in the next two slides here. Chemical reactions make and break chemical bonds. They lead to new arrangements of atoms. Starting molecules are obviously different than the ending ones, right? But the starting molecules here are called reactants. So if you take two molecules of hydrogen, right, H2, 1, 2, and have one molecule of diatomic oxygen, so two atoms of oxygen, and you put them together, once they react, you have products. Those products will yield, in this case anyway, two water molecules, right? So you can see that oxygen's no longer bonded together. They're in each molecule, right? Hydrogens are bonded to the oxygens and not to each other anymore. Very, very basic chemistry, but we got to start somewhere in this class, right? So I just want to make sure we review all this and make sure that everybody understands. Again, I'll say it one more time. If this is at all unfamiliar to you, or it's been a long time since you had chemistry or something like that, I will be happy to, during one of our online sessions, um, talk about this. And I'll let you know about the online sessions, as we get closer to Monday. It's Saturday morning right now, and I'm making these videos for you. So why does this matter to living things? Why do all of these things matter? I'm not going to get you to get together with a partner because we can't really. I could do breakout groups, but for this little question, I'm not really sure if it's worth it. Name at least two chemical reactions in your body in which new compounds are created, right? So if you think about it, what are you constantly making in your body? If you cut yourself, how does that heal, right? If you I don't know, when you cut your nails or your hair and it grows and you got to cut them again, I would say that would be new compounds, new chemical reactions happening in your body, right? Um, Anytime you're adding to your body or growing, hey, you go to the gym and you want to build up that six pack or those pecs or something like that, right? You're building muscle. That's all new compounds, right? So we'll be talking about how each one of these elements is formed into a compound that'll actually add to a living thing. I'm using humans here as an example, of course, right? But I think that's about it for this chapter. We're going to get into talking about water specifically and then carbon specifically, and that'll be posted. I'll probably work on those videos tomorrow. Not that you need to know that, I guess, but I hope you're having a great weekend. It's nice out. Get outside and light a bonfire outside tonight. It's going to be really nice. Sit out. It's going to be really cool and nice and low humidity. So have a great weekend, and see you in the next video.